So viewing birds as a resource to be exploited for humans. And if you were at a university with a wildlife program, any big state university, there would be courses and programs in management and exploitation of wildlife. And I went to for graduate, I went to a university that had one of these wildlife programs, so I used to interact with wildlife scientists more than I do, and they're a different crowd than non-applied scientists. But there's a lot of people that view wildlife as a resource for consumption. So if we view like a population of ducks or geese or whatever, there's consumptive use. And that's just what it sounds like. These are people who utilize that resource, and by utilizing it, consume it. And we're talking about mostly hunters here. That's a last 20, 30 years, that's an increasingly, the percentage of people who hunt has dropped. When I was a kid, my dad and I went hunting, but it's not something I enjoyed that much. We didn't do it much because went along with it when I was a kid, my grandpa too. Becoming less and less common. And maybe you have no family members that hunt or don't yourself, but there are a lot of hunters that are good people, and they appreciate the wildlife as they consume it, and lots are jerks too as well. And until about 25, 30 years ago, if we were talking about wildlife conservation, almost all the money in a state like California, New Mexico, Arizona, that was applied to conservation came from hunting licenses. These people, and fishing licenses, that's where the money came from. We didn't have, till 25, 30 years ago, this concept of non-game biology, non-exploited biology. So that's historically very, very important, and the deep tradition in a lot of American communities. There's also non-consumptive use of wildlife, which is kind of what we're going to do today. We're going to go out and we're going to look at it. And for birds, this is things like bird watching, which I want to talk about as we move on. People who are enjoying nature, studying nature, but not consuming it as part of their act. And an increasingly important part of the equation. The issue with these people is they don't pay licenses to do this. So they traditionally have not been contributing to the cost of conservation. Money has to come from someplace. For a very long time, it came from these guys. Example. This is a bird. It's in the parrot family, if I remember correctly. It's a tropical bird, and it extends its range into southern Arizona and New Mexico seasonally. And we'll talk about this again, there are people, these people, whose goal in life is to see as many birds as they can. And there are a significant number of people who come from around the Southwest, and they go to southeastern Arizona on the chance they'll see one of these birds and add it to their list in their bird watching. And I was in a group like that. I thought we were going backpacking. And when we got down there, I was with 3 people and said, no, the real reason we picked the Chiricahuas is we want to see a trogon. And, you know, we bought gasoline, we bought food, we paid our admission fees to the wilderness area, all for the chance of seeing that. We didn't. But we saw more hummingbirds than I've ever seen in my life. There's also commercial exploitation of birds. Modern times, it's mostly domestic fowl that are brought into captivity and inbred, and we use them to lay eggs, or we use them for their meat. You go back 100 years, and wild populations of birds of many species were exploited commercially. I can't think of any right now that are, at least not in North America, Europe. So with regard to conservation, let's look at that. Conservation is working to preserve the natural cycles and the natural populations of things as best we can in the face of growing human populations and human resource needs. When I look at conservation, I often look at conservation of biodiversity. That's the individual populations and species of birds or whatever. And here's a classic example of a conservation problem. This is the European starling. It's a European bird, and it was introduced to the United States in the late 1800s. And it found North America to its liking, and it's been expanding its range ever since. And everywhere European starlings show up in North America, our native birds suffer. It becomes a problem. They are very aggressive nesters, and they take nests away from native birds, and our native North American birds go, what, another European taking our habitat? But things like that, very simple things, can become conservation problems. A bunch of idiots brought a flock over to Central Park in the 1890s and released them because they wanted starlings in Central Park. Here's another conservation issue with California birds is a native North American bird. This is a bird native to other side of the Rockies, the Great Plains of North America, called a cowbird, a brown-headed cowbird. And not native to California, but they're out here now. The agricultural development out here has made the habitat ripe for them. And I don't know if someone brought them over, they flew over the mountain tower, they got here. But this is one of our native bird nests, and these are the eggs laid by that native bird. I don't know what bird, one of our native songbirds, and that's a cowbird egg. Now what cowbirds do is they find an unattended nest, female does, and she lays her egg in, and then she flies away, she's done. And that's her egg, and that little cowbird baby will hatch out very quickly before anyone else, and it'll push all the other eggs out of the nest. And then the mom and dad birds will raise a cowbird. And where these show up, native birds who aren't adapted to that, and our California birds aren't, are in trouble. And you'll see, conservation is sometimes difficult to explain to the public when you do it with shotguns. Because bird conservation in California often is walking up and down riverbeds or stream beds and shooting cowbirds. And that just doesn't, that's hard to explain to the public sometimes. With regard to conservation, we have something called the Endangered Species Act in the United States. This is legislation. And Friday, if we have time, I want to talk about other conservation issues, kind of close out the semester. But we have the Endangered Species Act of 1973, and it is a very powerful piece of legislation that was extremely carefully crafted and thought out. And when populations or species become rare and rare and rare, and they are at threat of disappearing, this act, properly applied, comes into play. Now we've got creeps in Washington right now. The head of the Interior Department, who would be in charge of running this, is hostile to anything that doesn't make oil companies money. And that includes endangered species. So it's horrifying what they're doing. They're ignoring the laws that were written and put into play. And it's not just a random thing. You can't say, oh, that's an endangered species. There's a series of steps that go into place. Like I said, very carefully thought out. Sometimes people in power say, well, you don't need to follow that. And they just say, well, stop following that. These things weren't arbitrarily put on that list. They were put there through careful consideration and public input. It takes years sometimes. And then sometimes people say, well, let's just cross this off the list. We don't have to worry about it. They do that with health regulations. They do it with conservation regulations. They do it with environmental regulations. It's frightening what they're doing. But we're off topic. We almost lost the Endangered Species Act when George Bush II was president because he thought maybe we shouldn't extend it. It did get extended. But this is a cartoon from when he was in the White House. Examples of the Endangered Species Act with birds in action would be the whooping crane. The whooping crane is a large crane. They migrate from the Gulf Coast into Canada back and forth. Every year, flocks of tens of thousands used to occur. In 1946, there were 13 birds. Agricultural use, pesticide use, people shooting them, 13. And it came under protection of the Endangered Species Act, and we brought this thing back. And these are sandhill cranes. That's a whooping crane right there. That's the power of these laws. That's a little bit of their biology. They would migrate back and forth from the Gulf Coast into the northern states and into Canada. And as they flew over these prairie states, the habitat for them was disrupted by agriculture and pesticides and people shooting them. And their numbers dwindled, and they had to become protected and had to set up refuges for them. And now instead of 13 of them, we have several thousand of them again. But that's the power of these laws when they're applied. And that's part of our natural heritage in the way that the Constitution is, in the way that Jamestown Fort is, in the way that an ancient church is. North American bird that is now extinct, that's kind of the poster child for bird conservation, would be the passenger pigeon. Passenger pigeon used to exist in this range here, flocks of birds that numbered in the hundreds of thousands. And between about 1870 and 1913, that's the last one that was alive, 1913 it died in a zoo, they went from hundreds of thousands of birds to one. And it was aggressive hunting, it was destruction of habitats, it was disruption of their breeding cycles. But we went from flocks of hundreds of thousands to one. That brings up in a lot of classes. I think it's kind of interesting. That's islands. And birds represent a nice example of island biology and conservation. We're going to do a whole day on islands one time. Islands are isolated habitats. And often, if they're isolated enough, the plants and animals that end up on those islands evolve independently of other islands in the mainland. And islands end up with unique things. Unique plants, unique animals. And birds are a great example of the bird species that have gone extinct in the last 500 years, things like this. Most of the bird species that have gone extinct have been on islands. Let's not put it that way. Put it another way. Island birds, not seabirds, but island birds, represent about 2% of the bird diversity. And they represent 40% of the bird extinctions. So we hit these isolated habitats pretty hard and lost a lot of bird diversity. When Europeans arrived in the Hawaiian Islands, there were 14, 15 species of honey creepers. Now there's 2. When Europeans arrived on an island in the Indian Ocean with this big turkey-sized bird, it was extinct within 60 years. The dodo bird. I found this online. If it's still up there, you could move your mouse around over these spots and it would tell you what bird it was talking about. But these are bird losses in the last 500 years. And look at the concentration on island habitats. Okay. Did that. Let me give you an urban wildlife bird story. And some of you have seen this, but I put this together a couple of years ago. Urban wildlife. We're now increasingly urban in North America and much parts of the world, so we have to find ways to share our habitat. It's hard to share the habitat with mountain lions, right? I know some of you said you've got them in your neighborhoods, but they are dangerous animals. Maybe some of the smaller things. It's a bobcat on campus. Dr. Rodriguez took that picture. The smaller bits of wildlife, we can, if we work with them, we can save some of this stuff, or at least have it around to enjoy. And this is my example from where I grew up, and this is something I noticed, put this together in my lifetime. I grew up in Albuquerque, and this is a postcard of Albuquerque about 60, 70 years ago, and this is what we're looking at here, this vast open habitat here. There's the city. So there's an aerial view of it in 2011, and there's the 60 years ago, there it is today. And I drew a line right here, okay, that vast open habitat there, and that's that line right there. Okay. In the last 50 years, that habitat has been lost. And Albuquerque runs up against Native American Pueblo land up there, so it stops. So, this is habitat we lost. Deer and elk even, and bears, and all sorts of smaller wildlife would have been using that habitat as they came in and out of the mountains. I grew up right there, in a house right there. And there it is. That's the lot in which my parents built the house. And that's a little piece of that natural habitat back there that my brother and I, spent several years till they covered it up with houses, playing on that habitat and knew everything about it. Yeah, that's me. So anyway, when we moved to that lot, this was the edge of Albuquerque. All this was open land. That's my high school right there, but that was there. But nothing else was here. We used to go out shooting out there. We used to go, model rockets. We'd fire model rockets right there. And we actually went shooting right there. That was our favorite spot. So, in the late 60s to now, this area all got filled up. The habitat disappeared. And all the wildlife it supports disappeared. But there are little fragments of it. And here, a good example. This is the habitat, like I said, I knew this really, really well. Because for about 5, 6 years, it was undeveloped. And this is the kind of things we found out there. And it's not bears and elk, but there was a lot of wildlife there. There were several species of lizards. that we could catch, and we did. And there were bunnies. You saw them regularly, and twice we caught an injured baby bunny and raised it up. And we had eagles sitting on the power lines in the backyard looking for those bunnies. And this is what I want to focus on. We had roadrunners. And they used to run around the backyard. They'd run along the fences. You'd see them in the streets. Roadrunners eat insects. They eat snakes and lizards. They eat this wildlife. That's their food. And as the habitat was transformed, we went from a scrubby, deserty habitat to green lawns and backyards and front yards. We went from this to this, and everybody had a lawn in the 60s and 70s. And that lawn doesn't support the same insects and the lizards and the snakes that the wildlife eats. The lizards disappeared, a lot of the native insects disappeared. And that is the very first year that we had Hot Wheels, by the way. That's my annoying little brother. He's telling us now, 50 years later, we're really getting into it. This all disappeared. We lost the insects that supported the lizards. We lost the birds that ate the lizards. And I was noticing when I was going back there visiting my parents that roadrunners started showing up again. And in like the early 2000s, I said to my mom, "There's a roadrunner in your yard." She said, "Yeah, I've been seeing him for a couple of years now." And I think it's a really neat lesson on wildlife biology and urban habitats. When we changed the habitat from this to this, we lost the life support system for things like roadrunners. Starting in the 1990s and the 2000s, people started taking the lawn out and putting it in the same house, putting the xeriscaping in, which we're encouraging you to do in Los Angeles now. You take that water-sucking lawn out and you put in natural habitat. And once this started to happen, we got native insects back. We got native reptiles back. And that's the food support system for the roadrunners. All these houses here, I put spots on this neighborhood. I know this because it's my neighborhood. All those spots, those are xeriscape yards out. This is, where's mine? That's my house right there. These were all grass in the 60s and 70s. Some of them still are. And now they're all xeriscaped. So we brought back an approximation of the desert habitat. And that approximation brought back the wildlife. Not the mountain lions, but at least some of the small wildlife. So, anyway, long story. But living with wildlife instead of opposing it. It's going to be hard to live with mountain lions, I agree with that. But we can live with small things. And I was walking with my mom last summer, and we were walking down here, right here, and a coyote ran down the street. I'd never seen a coyote in that neighborhood. Kind of scraggly looking coyote, but I said, "Is that a dog?" "No, that's a coyote." Look at this. With regard to bird conservation, bird watchers spend $40 billion a year on their hobby. 40 billion, that's a stunning number. That's binoculars, field guides, travel, and it's such a stunning number I footnoted it. One more example. This is the ivory-billed woodpecker. I think I uploaded the wrong version of this. I edited, no, never mind. Ivory-billed woodpecker went extinct in the 30s, we think. The woodpecker is about this big woodpecker, and it lived in swampy forests in the southeast. Southern states and up into Arkansas and Illinois, places like that, but it was a hardwood swamp forest creature, and when those forests were destroyed, it disappeared. This is Brinkley, Arkansas, along the Mississippi River. I'm guaranteeing you, none of you have been to Brinkley, right? There's no reason to go to Brinkley. It's a dying town, and once a Walmart went in nearby, all these businesses were ruined and they closed. There's not much in Brinkley. But Brinkley is really near a big Nature Conservancy property of this ancient hardwood swamp forest. And in 2002 or 3, some ornithologists, some bird guys were in there in a canoe, paddling through here, and they saw a flash of a bird, a big black and white bird, and they heard a bird call they'd never heard before. And bird people know bird calls like you know the voices of your family members. And the rumor started, not the rumor, their initial hypothesis was it was an ivory-billed woodpecker. Maybe. And that simple chance, people started coming to Brinkley and staying in the hotel. They set up a bed and breakfast, cafes opened, guides who would take you out in canoes, because all these bird people want to be the first person to get a photograph of an ivory-billed woodpecker. In 10 years, we haven't seen one, so it may have been just hope. There are people who come to Ventura County on the chance of seeing this bird. This is the Santa Cruz Island scrub jay. On the whole planet, it lives in one place, Santa Cruz Island. And there are people who come here, book a ride on island packers out to the island. They stay in a hotel or a bed and breakfast. They buy a few meals. They spend their money in Ventura, Santa Barbara County, go out there to see this bird. It's a measurable, maybe not huge, but it's a measurable amount of our economy, is things like this. So there's Santa Cruz. I'll tell you how to see him. This is Prisoner's Cove. You just get off the ferry there, you walk here. There's picnic tables there where they orient you before you're allowed to walk near the island. And you just sit down and you open up your knapsack and take out something quickly like crackers. And they come sit on the log next to you. The blue jays. They know that you're going to feed them. Anyway. Last thing on birds is a local bird resource. You guys are getting to the end of your careers at this campus, but this is a local resource here. The Western Foundation of Vertebrate Zoology is right up there off Pleasant Valley Road. It's it's one of the largest, if not the largest, private bird research institutes in the planet. They have one of the largest collection of bird skins. These are study specimens for scientists to use. That's what these cases are filled with. Privately held one in the world. They have the largest collection of bird eggs privately held in the world. They have the largest collection of bird nests privately held in the world, a very large library. That's a scientific research place. They have open houses once or twice a year. I usually post on Blackboard, so you can go visit there if you want. They're not open normally to the public. But they have taken interns. They have paid people. They've taken volunteers to work there over the years. So it's one of our resources. So anyway, where are we here? Birds. Theropod dinosaurs. Highly specialized for flight. All sorts of interesting aspects of biology. Any questions? And they're kind of neat. Okay. So that's it for birds. Let's finish up with mammals. We've got a week for mammals. We're done with that. Let's see. Mammals. Okay. That's mammalia. Mammals have hair. We'll get to about, synapomorphies for mammals, what defines them, but first off, all living animals, only mammals have hair, and all mammals have hair. All mammals have mammary glands. All living animals, only mammals have mammary glands, and all mammals have mammary glands. You're a mammal, so we maybe grasp their biology without even thinking about it better so than birds or other reptiles. As a group, mammals have put themselves into quite a variety of niches. There's a niche out there that works for a large animal or a small animal. There's probably a mammal using it. And all sorts of specializations, including flying mammals and hyper-specialized aquatic mammals, kind of more, generic mammals. If there's a food source out there, probably a mammal using it. In just one group of mammals, for example, bears, we have two extremes. We've got polar bears and tropical bears, just in one group of these creatures. By the way, the scientific name for the polar bear is Ursus, that's the bear genus, Ursus maritimus, the marine bear, because they spend a lot of time swimming. You know I like biggest and smallest. If you have to get it out, I'll tell you. That's the smallest living mammal. It's a bat from, I think, Borneo, if I remember correctly. Maybe Thailand, I can't remember now, I have to look it up. And that's a blue whale, the largest animal that's ever lived, which happens to be a mammal. You want some scale there. That little bat's 1.5 grams as an adult. That's 3-4 paper clips. And that's many, many orders of magnitude to get to a whale. Like many groups, we're still discovering new mammal diversity. Remember, I said that in birds we're finding relatively little new diversity just because we know birds so well. Mammals, there's new mammals discovered regularly, not as regular as fishes or insects certainly, but there's mammals out there we haven't seen before. Example, this is a deer, not a small deer, but a deer from Laos, Cambodia, in the highlands there. Just discovered 10, 15 years ago by scientists that local people knew about. They've been eating it for generations, but scientists hadn't seen it until just a few years ago. Look at this little mouse here. Moose is the European mouse genus Cypriacus. That's the island of Cyprus. Can you picture Cyprus? That island off the coast of Lebanon, Israel? Yeah, there's a mouse that was hiding there no one had noticed before. So, and then this is a tiny little rainforest insectivore from the Congo. So there's mammals in obscure places where we might expect to find unexpected things, but also hiding out in the open. A lot of mammals have been domesticated for all sorts of reasons. Domestication is when we bring them into captivity, we tame them, we interbreed them, we selectively breed them for things we like. Certainly, a lot of mammals producing food resources for us. Other things like leather. Mammals are used in scientific research, and then many, many are used as companions. As a resource, mammals are exploited. Again, I can't think of it in the modern era. The exploitation of wild mammals is not nearly as common as it was maybe 200 years ago. But we have used them as resources. I don't know if you can tell what this is. It's an American bison. I don't know if you can tell what this is. These are bison skulls.
Jeez.
That was in the 1880s when our forebears went out in the Great Plains and destroyed those herds of bison. Several million animals large, some of those herds. It's a concerted effort to do that. Of the wild mammal populations still exploited would be whales by certain cultures and treaties still to this day. So let's look about where mammals come from. So, mammals come out of, here's our mammal, there's the ancestors, that primitive amniote type creature. Let's look at that. So if we review a little bit, we're well done with the Paleozoic, purple down here. That was the age of fishes. The Mesozoic, which we spent a lot of time on, that's the age of reptiles, or we can call it the age of diapsids. And then the modern era is the Cenozoic, and we often call it the age of mammals. Mammals have a diversified mass period. And if we look at our amniotes again, here's our evolutionary tree with time across the bottom here. There's all the amniotes. We got all these things we call reptiles here, and then the mammals over here. Mammals have their base way down those early synapsids, and by the Triassic we start to have things we might start calling mammals or proto-mammals. So mammals go way back. They go back as far as the root of dinosaurs go back. So, there's our mammal lineage, and there's, just zooming it up here, and there's some of that fossil stuff, the ancient stuff. These are living things out here. So if you look back here, the Triassic, in the middle of Triassic, we have things we would call mammals or almost mammals. And again, that's about when we start getting dinosaurs. So it's a group that spent most of the Mesozoic hiding from the dinosaurs. So anyway, mammals are the synapsids. So we want to focus in on that. We're finished with the diapsids. Remember the synapse, well, we'll find in a minute. They have that different kind of skull. So we have that synapsid ancestor, diversified a couple different ways, a bunch of fossil stuff that we don't have with us anymore. And one lineage survived and spread out, and that's what gives us mammals. Now you run into this, I can't remember if your textbook uses it, but you run into this phrase all the time. This is a PowerPoint slide I found from someone's PowerPoint. Mesozoic era mammals evolved from mammal-like reptiles. There's no such thing as mammal-like reptiles. That's not a concept that we use anymore or shouldn't be using. Mammals did not evolve from reptiles. But look at our evolutionary tree here. There's the mammal line, synapsid line. There's the reptile line, the diapsid line. This thing was not a reptile. We don't have mammals coming off reptiles. It looked more like a reptile than anything else alive today. But we don't call those things reptiles anymore. This thing was not a reptile. So, if I slip and say mammal-like reptile, you can correct me. So let's just look at the synapsids. There we go. The synapsida. Did that. So there it is. There's our evolutionary tree. And we're going to walk through this and look at some of these traits along the way and some of these creatures along the way. Here's the mammals in the modern sense. These are the living groups here. And then there's this cool fossil stuff that leads up to there. And again, we've got traits here. We'll touch some of them, not all of them. But these traits, this is how I focus on this diversity of this history. These traits give us a peek into the biology of that creature. Is there some new niche? Is there some new way of exploiting an old niche that we see with these traits? Because these traits are adaptations. So we focus on those. Or I do at least. So I found this cool picture. There's the mammal line. There's a primitive synapsid, not a reptile, towards mammals. And we had we had only 2 synapsid in lab last week, our old plastic dinosaur lab. And I went around the tables, I think I said, Aaron, I held up this little guy here. And I said, doesn't even look like a dinosaur, does he? Just his face, his teeth, not dinosaur-like. So, let's look at some of the history there. There's all sorts of stuff going on with the jaws in terms of the teeth and the roof of the mouth called the palate. All sorts of stuff happening at the back end of the jaw that we have a look at. In general, some of the trends we see are, and we've seen these trends before. We saw these in the diapsids, but one of the important ones is increased mobility. We're moving around more. So some of the correlates with that are higher metabolism. And higher metabolism leads to warm-bloodedness, right? Lighter weight, more agile construction. All play into increased mobility. And we go from, a goofy, ancient, proto-synapsid or early synapsid to more dynamic creatures, which we think of. We think of mammals today. And again, we get all those physiological changes. We get going from cold-blooded to warm-blooded. We get the circulatory system being jerked around to accommodate that. We get the respiratory system being modified to accommodate that. The jaw modifications, and we don't do a whole lot of detailed anatomy in this class. This is one place where I stop and do some, and I rearranged it again this morning. It's not that complicated, but it's involved. And what we see from primitive to advanced, we see all sorts of jaw modifications, and we see differences in how the teeth are arranged. That's important, how you interact with your food. We also see modifications, particularly to the hinge of the jaw. You have a very simple jaw hinge as a modern mammal, compared to a fish, certainly, and compared to a primitive synapsid or a diapsid. Your jaw hinge is really strong, but really, really simple. And there's a transition that's kind of interesting. Well, I think it's kind of interesting. Maybe you will too. We'll look at that. There's all sorts of brain and sensory modifications as well. Certain mammal senses become well developed, and centers of the brain involved with those are developed as well. So we can, we'll do that later. Did that there. Okay. Well, I don't know, I find these online. I like these. These are It's just a title slide here, but there's hypothesis of mammalian, or synapsid, I should say, evolution. We'll meet some of these guys along the way, these cute things here, leading towards mammals. There's some of the history there. And I pulled this offline, and it's derived from a popular Science magazine article. And, oh, look at that. That just jumped right out at me. Reptiles did not become mammals. But in the popular literature, even 30 years ago, they're still saying that. Okay, there's our evolutionary tree. And I thought we'd meet some of these cool creatures along the way. So the starting point of the synapsid line, these are all the synapsids. The starting point of the synapsid line is that synapsid skull, which we talked about when we talked about skull diversification. That's where we start. And so here's the amniote skulls. We've got a primitive amniote. We've got the mammal crowd. We've got reptiles and birds. And we can just leave birds off and just say reptiles. And remember those skulls, the one with no openings? That's the primitive version. And then it splits and goes two routes. One route opens up one opening, and the other lineage opens up two. We've done those guys, here we are. And so that's the classic synapsid skull in cartoon form. And again, remember that opening is all about more flexibility in those jaw muscles. Those jaw muscles can come from the back of the jaw, they go through this opening, they can spread out across the top of the skull. So here's some of the players in our story, some of the creatures we want to look at. These are obviously reconstructions. So I kind of simplified that. This is, where is it here? Well, I have to go back here. There's that right there. Kind of made a little simplified version of it right here. So we've got these guys giving way to these guys, giving way to these guys, giving way to mammals. We'll start there at the bottom. There's a group down here at the bottom. It's again, one of those groups that's not well defined, so it's got multiple lines on our evolutionary tree, not necessarily a monophyletic group. They're down here, they're called they're down here at the bottom here, and they're called pelecosaurs with quotes around it. I have to look up and see what peleca means. It means lizard again. But this is a really early synapsid. And what's he look like?
A lizard?
A lizard. Remember that lizard, we call the lizard anatomy, is kind of primitive amniote anatomy. So we see that basic lizard anatomy anywhere. If you caught that, you would have no hesitation, like, oh, it's a lizard, it's a reptile. But this little guy is running around the Triassic or the Permian, probably the Permian, with a synapsid skull. And so that's these little guys down here, pelecosaurs and their relatives. So there's a step up there. These are see, you've got multiple lines. That means we don't know what's going on there. That little lizard leg down here. And then there's a step up. The things we call pelecosaurs. True pelecosaurs. We didn't put quotes around it. There's some reconstruction of these silly things. Again, kind of lizard-like. And Dimetrodon is in this crowd. Dimetrodon is a pelecosaur, not a dinosaur. A pelecosaur. And we've talked about that before in other contexts. The big fin on the back. You're asking me in lab what that was about. I don't know. We can hypothesize. It was about displaying to each other. I think that's probably likely, but I also think just as likely, he gets up in the morning and stands with that facing the sun and warms his blood up as the blood moves in there. In the middle of the day, when he's a little bit too hot, he stands the other way, and that becomes a heat radiator. So it may have been about thermoregulation. Other things we see with these pelecosaurs now, we start to see the skull. We start the diversification of the skull. And one of the things we see is these nice, beautiful, we see teeth, instead of all the teeth being almost exactly the same, like in a crocodile, we see diversification of teeth. And one of the first places we see it is canine teeth show up in pelecosaurs. The other thing here, this is the roof of the mouth. Can you picture that? This is Dimetrodon's mouth. And there's his big canine teeth there. This is the palate, the roof of your mouth. And remember, we've got, these aren't them, these are something different, but remember we've got the nostril leading into that, right? Okay. So the palate starts to become closed off, and we'll see this again, but the palate is, the bones of the palate are squeezing in and creating a separate channel above the mouth cavity for the air to flow. like a frog. You saw the frog in the lab. When your frog, the frog pulls air through its nose and it's right inside its mouth. You don't do that. And you've got this separation between where the air flows and where the food flows. And that's starting to occur here. And there's Dimetrodon. I'd love to get a Dimetrodon skull for lab, but it's like $600. So we haven't invested in that. But that's a classic synapsid skull with that beautiful, well-formed single opening there. We don't have anything alive today with that clean synapsid skull like that. So, just to contrast, we spent a lot of time with diapsids. There's a dinosaur. There is a synapsid. There's a diapsid. There's a synapsid. And they don't even look the same. The jaw arrangement's becoming more complex. The temporal region very, very different. That's a reptile. That's a proto-mammal. Okay. So, we're bouncing up a little bit. Okay. A group called therapsids. Another extinct group, or no good members of it left. Next step up in our evolutionary thing, and there's some of the traits we see here. Let's look and see what we're doing here. We are becoming, well, let's look at the traits. There's some reconstructions of therapsids. We're not even trying to draw them like dinosaurs anymore. There's some more reconstructions. I like these silly things. What are we seeing? Oh, there's a skull. It's a beautiful skull there. Look at the big temporal opening there. The muscles from back here pass through that opening and spread out on top of the skull there. And look at those big canine teeth. So we see a couple things here that are suggesting a niche expansion. The lower jaw musculature is expanded. In particular, you get a large expanse on the back of the jaw here for those muscles to insert on. These guys were biting and probably had a really powerful bite. I summarized a bunch of other characters and brain modifications. You get a nice three-finger skull, you can get an idea of what the brain was like on the inside. In particular, certain parts of the skull are becoming expanded and bigger. And these are parts of the brain are becoming expanded and bigger. And these are parts of the brain that are going to play into mammalian biology. Hearing, for example, and smelling, and balance. More agile, more mobile. The trend we see in all sorts of groups here. And evidence of that is a more upright gait. Gait is your walk, how you interact with the ground. And in therapsids, we start to see the limbs, and we're tetrapods, we have 4 feet on the ground. We start to see the limbs, instead of walking like this, out sprawled, the limbs are coming under the body. We saw this in dinosaurs too, right? And the mass of the body is now focused more directly straight down. The easiest force to manage when you're managing weight is vertical. And been to Europe and look at cathedrals in Europe? You can't do it. In the Middle Ages, they built, you've seen pictures of huge cathedrals like Notre Dame and places like that. The medieval architects were brilliant at managing force. And those big stone arches, they focused all that weight onto vertical pillars. They're brilliant at it. And that's what evolution is doing to these creatures. It's taking the mass and focusing it up and down. So the older, more primitive sprawling gait, like you see in most lizards, like you see in Dimetrodon, the legs are out like this. It works, but there's a better way to do it. And that's pulling the legs in. And so we have modifications to the girdles, we have modification to the pelvic pectoral girdle, modifications to the limbs. Keep moving on. Okay, on the road to mammals. Cynodonts. Dont means teeth. I need to look up cyno. Cynodonts are the next group up. And here's reconstructions of them. So there's some of the traits. Let's look at a few of these. And again, the double line, triple line tells you there's a bunch of creatures there. We're not exactly sure how to arrange them yet. A diverse group. Cynodonts are actually, think about them, an advanced version of therapsids. They come right out of therapsids. No, that's classification, I guess we don't really need. What they are is they're increasingly mammal-like. There's a recovered skull, and there's a reconstruction of this little guy. Most of these things are fairly small, by the way, at this point. But look at that skull. That just doesn't look like a lizard skull or a dinosaur skull. And then, I know you haven't looked at a ton of skulls, but we looked at some of it last week. That's looking much, much more mammal-like. So here is just a skeleton. I just threw this in here. The more detail here we want to deal with here, but these are some of the things we're seeing. And these cynodonts are holding on to some old-fashioned stuff. This primitive character is the red. That's stuff that more primitive synapsids have, like Dimetrodon, like therapsids, that mammals don't. And then purple, these are some things that are more mammal-like. So we've got a nice transitional thing here, hanging on to some of the old-fashioned stuff, showing some more mammalian stuff. So examples of what we're seeing here. The lower jaw, focus here on the lower jaw. The main bone of the lower jaw is the dentary. It's been that way since fishes. The main bone of the lower jaw is the dentary. Now, in fishes and everything up to now, in dinosaurs, everything up to now, there's all sorts of bones in the back end of the dentary that connect the dentary to the skull. These are the articular bones. And these things start to lose that function. They start to become less and less function as the what's the word I'm looking for? The fusion, no, that's not the right word, the articulation between the dentary and the skull, that's their job. They start to lose that. And the dentary gets bigger and bigger and bigger and bigger. These bones get smaller and smaller and smaller and smaller. Okay, we'll look at that in a little bit. So dentary becomes more important, the post-dentary bones are reduced. And if you look at primitive cynodont here, and a more advanced one here, there's the dentary, and it's all this junk back here. The dentary is now starting to articulate directly with the skull, not through these silly bones. These bones start to lose that function. And they play a very important role in mammals. You still have them. The palate. Remember we saw in Dimetrodon, the Palaeosaurus, the palate start to close in? It's now fully complete, and we have a hard palate here. That's this. So that, again, that's not the nostrils that are up here, but the air comes in through the nostrils and it passes in a chamber here, the sinus cavity, back towards the throat. And this is there's a fossil of one of these early cynodonts, and that's what we're talking about. So the air comes in at the nostril, goes through here, and all the way back here. This area wasn't enclosed up to now, and more like this. This is the old-fashioned way of doing things. And there's where the air would flow, and this is what's new here. So we're breathing more efficiently. We can separate food from air. We probably choke to death fewer times with this arrangement here. And then think about niche there. We're breathing more efficiently. Or there's been selective pressure to get you to breathe more efficiently. Breathing more efficiently means more oxygen. Why do you need more oxygen? You're more active. Maybe you're warm-blooded. These are suggestions of warm-bloodedness, or at least activity. And this is a bunny, and this is what we're talking about here. It's this part of the roof of the mouth. This is fully developed in a mammal like you, but the air goes down this yellow line here, and the food and water go here, and we've completely separated those. You've got a hard palate towards the back and a soft palate. I think people who snore, this flap of tissue is what's vibrating when you snore. We're seeing dietary diversification. The post-canine teeth, the canine teeth up front, the post-canine teeth, well developed, and they start to diversify in structure as well. What's gnathos mean? Here's the genus name. What's gnathos mean?
Jaw.
Jaws. I'm not sure. I need to look up Macetognathus. And again, this is neurobiology or neuroanatomy, and I'm not up on it, so I kind of summarized a bunch of traits here down into the brain case is more mammal-like. The brain case is the part of the skull where the brain resides, called the brain case, and it's actually bulging out, very unreptilian or diapsid-like, much more mammal-like. So parts of the brain that mammals are developing are becoming bigger and bigger, and the skull reflects that. We can see that in the anatomy. Okay, let's take a few minutes here.